So now we are proving this embedding lemma. So we have H, which has vertices in, say, let's draw it this way: x1, x2, x3, and x4, x5, so on. And G has a vertex set in V1, V2, V3, V4, and V5. And we want to embed the vertices here into here, while if these two, there is an edge, then we want to embed those two into the two vertices here, which is also adjacent. So roughly how we want to proceed is that we want to keep track of, where each vertex can be embedded to. So this vertex can be embedded to any vertex here. And also we have this vertex, which is adjacent, and this can be also embedded to any vertex in here. But as soon as you embed this one vertex to here, so now this vertex can only be embedded to neighborhood of this V. Say this is X and Y. And before, Y could be embedded to any vertex in V2, but now it can be only embedded to the neighbors of V. So N, G, V, intersection with V2. So before this has a larger candidate set, but now that candidate set shrink. So how we want to proceed is that we want to make the choice. So when we embed this, this vertex to here, we want to make sure that we embed this to some proper vertex, which does not shrink this candidate set too much. So we make the choice so that this doesn't shrink too much. And every time we keep track of, how each candidate set shrink. And then we want to keep track, make sure that it doesn't shrink too much. So that's our idea. And whenever we make the choice that doesn't shrink the candidate set for other vertices. And then there we use this previous lemma. Roughly, there was a candidate set for this Y, and then now we want to embed this X into certain V. But when we do that, we want to make sure that it has lots of neighbors here. So this candidate set for Y is the B prime here. So this is some set B prime. And then now we want to embed the X into some vertex V, which satisfies that the shrinking doesn't happen too much. So this is the B prime now will become this new set. If we embed X into A, then B prime will be updated to smaller candidate set. Because now this is say A, then only the neighbors of A inside of B prime is our next candidate set. But we want to make sure that it doesn't shrink too much. So we want to choose this A out of A from not here. So these are the bad things, but this says that there are not many bad choices. So we can make a good choice. Let x sub 1 to xh be an arbitrary ordering of the vertices of H. And let, say, psi of I be the index such that xi is inside of x psi I. So we give some ordering, and then we want to keep track of whether each vertex belong to which set. We will construct an embedding pi by selecting images, say V1, which is the image of V1, X1, and V2 is imaging of X2, and so on, one by one. And let C sub I, J be the set of possible candidate of Pj. So meaning that the Xj can be embedded to here at the time right after we have determined P1 to Pj minus Pi minus 1. So we want to embed Xi now. Let's say this is X1, and this is X2, and this is X3, X4, say X5. And now we have embedded these two here we have P1, and here we have P2. These two are embedded. And then now we want to embed P3, X3 into here. So this is the C3 3. And then X4 has a candidate set here, C3, 4. So at this picture, I mean X3 has only one earlier neighbor. So the only restriction here is that we have to embed these vertices into neighbors of V1. So C33 is exactly the neighbor of V1 inside of this P3. So I mean this is the how we denote the candidate set. And as we want to embed Xi into Bi, we initially have C1j is just a V psi j. So V psi j is that if we have X6 here, psi 6 is 3, meaning that the X6 is inside of X3. So that's where we want to embed. So initially, this entire set is our candidate. Assume we have already determined P1 to Pi minus 1. And we have this Ci j is at least delta plus 1 times epsilon n for all not yet embedded vertices xj. So this assumption is true when I is 1. When I is 1 for all j, each candidate set has size n, at least n. So because of this assumption it has size n, and because of this assumption, delta plus 1 times epsilon times n is smaller than n. So initially this holds. So assume that this still holds after I step. Now we want to show that with one more step, by increasing I by 1, we embed Bi, and then we can still make this satisfy for the I plus 1. Then we can keep embed until we cannot. I mean, until the end. So we want to embed, okay, let's say select this vi. So we want to embed xi into vi from this ci I. And let A be the neighbors of this xi, which is not yet embedded. Let's say they are xs1, xs2, xsp. So in this case, if this x3 has only one neighbor, say x4 and then say x7, then A is x3, x4 and x7. Because x1 is also a neighbor, but it is already embedded. So these two. So we consider this because now when we embed x3 into one of the vertices here, now we need to make sure that the candidate set for these vertices, we need to make sure that candidate set for these vertices does not shrink too much. So this x4 has a candidate set, and then by embedding this, x3 to here, now only the neighbors of this inside of this set is the new candidate set. It's updated. On the other hand, for x5, it has a candidate set here. Because there is no edge between x3 and x4, even if you embed x3, this, any vertex here is still fine. It puts no restriction after you embed x3. So that's why we keep track of this A, which is the vertices whose candidate set will be updated after we embed xi. But what do we know? Now we want to embed this into here, one of this set. But we know that this pair is epsilon regular. So since for each of these, V psi I and V psi SL is epsilon d prime bt plus regular. This is epsilon regular with the density LSD for all L between 1 and P. So what does this previous lemma says? This previous lemma says most of the vertices here has a correct degree to here. So only small portion which may not have the correct degree to here, then you take out the small portion, and then this remaining part is our good choice. So previous lemma implies that all but at most epsilon n vertices in at most that many vertices in this set has a long degree. That means at most that many vertices in this current candidate set have long degree. So rest of them has at least t minus epsilon times ci sl neighbors in ci sl. So we actually apply the lemma. Okay, let's just say we apply the lemma in this form. so that we don't have to consider about this 2. So I mean, instead of 2, we can just consider epsilon here. So the vertices with 2 small degrees are at most epsilon, so rest of them are has a high enough degree. So that means, so this is true for one each L, and then there are p many L. So meaning that when we embed this to here, we have to consider that we have to exclude certain small set, which if we embed this to here, then this will shrink too much. And also we have to exclude certain set which will shrink this set too much. So there are, I mean, at most delta many sets. So here p many sets that we have to consider. Hence L list C sub I minus delta times epsilon n, which is L list epsilon n vertices. In this CII has L list, say D minus epsilon times CISL labels in C sub ISL for all L inside of L between 1 and P. And among them, we know that at most epsilon and minus 1 vertices are already the vertices which we use to embed other. So here we are embedding x3, but later when we embed x6, we want to avoid b3 here, which was already choice of x3, because we want our map to be injective. But how many vertices do we embed here? This is at most epsilon n. And this one vertex is still we are considering to embed, so meaning that we haven't embedded it yet. So rest of them are at most epsilon n minus 1 vertices are already embedded. So out of all the candidate set, I mean, delta times epsilon n may not be a good choice, and epsilon n minus 1 also may not be a good choice because it's already, I mean, occupied. Then we assume that this condition, from that we know that there is at least one choice. Thus we can choose one of such vertex as Pi, which is not inside of, already embedded vertices, which has at least t minus epsilon times Ci SL labels in CISL for all L. Then we embed Xi into Vi, and we update Xi plus 1j is for all those vertices in A, we update it by, we shrink, and rest of them we just keep them. Okay, we just keep that. Then this will shrink the factor, shrink this set by a multiplicative factor of d minus epsilon. And each set here, so this is not yet embedded, and it has this candidate set. And while embedding previous one, this can successively shrink a few times. But how many times does it shrink? Every time its neighbor is embedded, it shrink, and its neighbor embedded, it shrink. So it shrink at most delta times, because it has maximum degree at most delta. As xj has at most delta neighbors, one thing to notice that here, I mean, we could have deleted bi from this candidate set, but which is not really necessary, because in any way, when we choose next vertex from this candidate set, we exclude this, I mean, previously embedded vertices. So, I mean, even if we don't delete here bi, we can still make the map as embedding injective. So, I mean, we just keep it here. So, as xj has at most that many neighbors, we have that for all j which is bigger than I, this Cij has at most this size. And by our choice of epsilon, I mean, we get this inequality. Thus, we can choose pi, so as long as I is at most h. So this is the condition that we wanted to get. So what was the condition that we assume? We assume that we have embedded the vertices, so that for the all unembedded one, each candidate set has size at least delta plus 1 times epsilon n. And then we embedded one more, and this is still true. So we can keep embed one more and one more while keeping the condition true. So by repeating this, we can select P1 to PH, and this yields a desired embedding. So this shows that this embedding lemma, saying that once we have this regularity partition, then it's easy to find our desirable subgraph H inside of that, as long as it has bounded degree, and then it has a correct partition, and it is not too big. So we can actually use this and regularity lemma together to prove several statements. So one of them is the Erydish-Stone-Simonovich theorem that we have proved before. We can also prove it using this regularity lemma. And then also we can use it to prove certain statement in Lemji number. Yeah, we will do that in the next video.